Welcome to another video. Our previous video introduced JuMP in Julia and showed in a coding demonstration how it fared compared to the way that we've done it so far with Optim.jl. And we also showed how adding a couple of lines of code to our existing JuMP code was able to impose a pretty versatile set of constraints. And in this video, I wanted to take a little bit of a deeper look under the hood of what's happening when we do this sort of constrained optimization and show how we can impose the same constraints in an Optim-based code pipeline. I also want to cover how we can adjust the Optim.jl code pipeline to include analytical gradients, and that this can speed up the optimization substantially. As we showed in the last video in the demonstration, it's very easy to add a constraint to JuMP. In particular, we added just one or two lines that imposed the constraints that we had in mind. But this is trickier to do if we're doing Optim.jl. And we need to basically treat the constrained parameter as data instead of a parameter to be optimized. And so that can be a little bit tricky from a coding perspective. And we also need to take whatever parameters are constrained out of the vector, which might cause us some indexing headaches if we're having to re-index the parameters that are being optimized separately from the ones that are being constrained. And then inside the likelihood, once we've sort of done that re-indexing, then we need to impose the constraint. And then we also need to repeat all of these steps afterwards once our estimates have been obtained, so we can make sure that the estimates are consistent with the constraints that we're imposing. So thinking back to the last video, we went through an example with JuMP and we showed that it gave the right point estimates, but it gave incorrect standard errors that had complex numbers in them. And we commented on how the standard deviation or the standard error of beta 2 should be 0 if it's constrained to be a particular value. And then we also commented that the constrained log likelihood was lower than the unconstrained log likelihood, which is consistent with econometric theory. Now let's talk about how we would do this in Optim.jl. And in this case, it's helpful to create a matrix that is a helper matrix that stores the information about the constraints. So every row of this matrix will be one constraint, and there will be 5 columns. The first column will tell us the parameter index that we intend, of the parameter we intend to constrain. The second column will be the index of another parameter that enters the constraint. So if this is like beta 2 equals negative beta 1, we would have 2 and 1 be in these 2 columns. If it's just a fixed value, we can just ignore the index. And then we can specify 2 types of constraints, one that it's equal to a fixed value, and we could index that by 0, or we can index it by 1, which means it's a function of some other parameter. And then we could have a column storing information about the multiplier. So for example, if it's beta 2 equal negative beta 1, then negative 1 would be the multiplier. In the example we did in the last video with the coding demonstration, we specified beta 4 equal 1 plus 2 times beta 3. And then we can also have a constant m. So in this example, it would be positive 1 for m, and q would be equal to positive 2. So we can store all of our constraints in this manner, and I should emphasize that these are all linear constraints. If we wanted to have nonlinear constraints like beta 4 equals exp of beta 3, I don't think that this approach can be useful for that. But that's not to say that we couldn't come up with an approach that could handle that with Optim.jl. So for the examples that we've gone through in this video, we have one constraint. Our first constraint is that beta 2 is equal to 0.16. And then our second constraint is that beta 4 is equal to 1 times beta 3, 1 plus 2 times beta 3. And then this one here is showing the type of the constraint. And over here, that was 0. So basically, the middle 3 columns can be 0 if I'm just setting this parameter to be a fixed value. And in most cases, I'm going to want to restrict coefficients to be equal to each other or equal to 0, which means they drop out of the model. And so those are going to be the most common constraints I'm going to impose, and that's why this approach can be useful for imposing a lot of constraints. Let's do a brief coding demonstration that shows this in action for the problem that we were doing in the previous video. And I've got the same code base as the previous video. I'm just going to go down to where we are now. So we just did the constrained optimization using JuMP in the previous video, and then I've got the constrained optimization using Optim for this current video. And this is setting up that matrix that I just walked you through in the slides. So our matrix is going to be beta 2 is equal to 0.16, beta 4 is equal to 1 plus 2 times beta 3. So how does this work? Well, I read in my parameter vector and re-index it, and then I impose the constraints. And what I have to do is I have to insert the parameter values that are not being estimated. And why do I have to insert them? Well, because this parameter vector theta that I'm reading in, that needs to be stuff that is being optimized over. I can't have any constants in there. The constants need to be treated as data, which is why this constraint matrix is being treated as data in the likelihood optimization. So any parameter that's a constant, I need to insert, and then I can come up with formulas for like what part of the parameter vector they need to be inserted in based on where they are in this constraint matrix, right? So the first column is going to have index 1, and the second column is going to have index 2, right? And index 1 is going to be what I need to insert into the parameter vector. So once I've done those insertions, then I have all of my coefficients on the basis that they need to be to just do the linear algebra to specify the objective function. And then when I specify my starting values, I need to delete those parameters that are going to be inserted inside the objective function. So again, when I pass the starting values to the optimizer, I should only be giving it the parameters that are going to vary with the maximization routine. Then everything else is pretty standard. And then I want to make sure that I get the Hessian on the stuff that's been varying with the optimization. And then later on, I can add back in to the parameter vector the estimates, and to the standard errors, I can just put in 0 if it's a fixed value, or the standard error of the other parameter that was estimated if it's an equality constraint. And then I can just store these all in a data frame and see what we get. So I'm going to add a breakpoint, and our optimization is finished. It took a little bit more iterations to get through, but it converged, and it appears to have converged to the exact same values that the JuMP did. And here we actually have good standard errors because we sort of handled that on the back end very particularly in the way that we needed to. So these standard errors are valid, whereas the JuMP ones were not. But obviously we spent a little more time in the code to make things match up nicely. And that wasn't necessarily the case with JuMP. JuMP we didn't need to do so much prep work, but then it gave us the wrong standard errors. And so which one's better? It's kind of a wash. Now let's go back to the slides and talk about supplying an analytical gradient, and then do a demonstration about that as well. So let's talk about analytical gradients and Hessians. So far in the demonstrations that we've done, we've relied on Julia's automatic differentiation to provide the gradient and Hessian for our optimization. And that will provide a decent speed up relative to other optimizers and other software packages on the market. But it still might be useful to make even greater performance gains by specifying the analytical gradient of the likelihood, if we can. So our goal is to provide a helper function to Optim.jl that specifies the analytical gradient of the problem. And then the optimizer can just read from that function instead of trying to do its own optimization or to do its own differentiation that will take some other computing power to do. And the gains for this seem to be pretty large, at least in my experience. I once tried this out and it seemed to give a 3x speed gain. That advantage with the analytical gradient is going to be very problem specific. If I just have a simple linear regression model that I'm estimating with a normal MLE, that's not going to provide much speed gain relative to a numerical or an automatic differentiation, because the problem is just easy to solve. I can get the answer from linear algebra. But if I have a really involved logit model with a lot of parameters, it could actually provide a drastic speed up. So let's go back to the code and see how we can provide an analytical gradient and see what kind of speed up we get. And I've got the same script that I've been using for the other demonstrations in this mini-series. If we go down, we can see where the analytical gradient enters. And here I'm writing a function that's wrapping the optim call and the likelihood function into it as sub-functions. So this is a pretty optimized piece of code. We don't need to go through every little feature, but it's got a number of features in terms of specifying how the problem is set up for a basic multinomial logit or a conditional logit. And basically the main idea is that I have a function or a sub-function that just takes the parameters, and this is going to be my likelihood function. So I'm going to get to the bottom of this function. I'm going to have a likelihood expression. And then I have the gradient function, which is specified as G exclamation point, which means it operates on the parameters in place. And then for this, I'm going to specify what the gradient is. So for the multinomial logit, if I generate the choice probabilities, then the derivative of the log likelihood with respect to the betas, the coefficients on the x's, is minus x prime times d minus p. And here I have an option to do weighted MLE, which is why this W is there. And then the gradient for the alternative specific coefficients, which is typically the Z times gamma that we've shown earlier, that's going to be a function of D and P, but it's also going to be a function of the different Z's. So it's it's similar to the minus x prime times d minus p, but it's a little bit different, or at least I chose to do the expression a little bit differently. And then making sure the parameter indices match up is important, but it's a little bit hairy for this problem, so we don't need to really go through it. And then we just tell it that we have a twice differentiable object with objective function f and gradient g. And then we can have it do the normal optimization options and then return our estimates to us. And in particular, I've gone through and had it return the standard errors. So this custom function that I wrote, you give it the data and the starting values and the other characteristics of the problem, and then it will return to you the estimates and the standard errors, the objective function value, and the gradient vector. So this is sort of like a way to get similar to a stata command where it kind of gives you the cleaned output in the way that you want. And then we can just estimate this on the same data set that we did the mixed logit practicing on, and that's going to be available right there. So I'm going to run this file start to finish since it doesn't take too long, and we'll see what pops out. Looks like it finished. If we look at the iteration log, it looks like it took about 14 seconds to do this. That's a lot faster than when we did it before, especially because I started from really bad starting values. And the estimates to my eye look pretty similar to what I saw when we did it without the analytical gradient in the past. And so that's how you would be able to speed up your optimization by using an analytical gradient. So that is a little bit about how to impose constraints and how to supply an analytical gradient to your optimization in Julia. I hope that you've found these principles interesting and that you've learned something new. Our next video, which will be the last in this mini-series, will introduce the idea of mathematical programming with equilibrium constraints, or MPEC, and show how it can be useful to further speed up the estimation of some complicated structural models. Thanks for joining this one, and I hope to see you in that last video.